So, what comes to your mind when you hear El Nino? I like to ask that question in all of my classes whenever I talk about El Nino, and usually the answers are somewhat pretty similar. I hear things like it's a storm, or it is some kind of hurricane, or something like that. And here in California, where I'm recording this video, this is typically what we associate El Nino with. We typically associate it with stormy weather. We typically associate it with things like more rainfall, faster winds, just crazier weather. But believe it or not, that's not true for everywhere here on Earth. So what we're going to do in this investigation is we're actually going to uncover what El Nino is, what La Nina is, and what this whole circulation pattern is. So the goals for this lab, first we're going to talk about something called the Walker circulation. Then we're going to talk about the conditions that lead to El Nino and La Nina, and then I'm going to have you looking at something called a Tau Triton Array. And it has some really cool data that helps us determine, are we in an El Nino or are we in a La Nina? Alright, so grab a drink, strap in, let's do this. Okay, so first, let's talk about where this all comes from. So, there is a global circulation. So, last class I talked about what's called the jet stream. That's a type of global circulation. Well, there's another type of global circulation that takes place in the equatorial Pacific called the Walker circulation. So here's how it works. Along the entire equator, there is this band of winds called the trade winds. And the trade winds blow from east to west. Very different than the jet stream, which blows from west to east. The trade winds blow from east to west. Now, as they're blowing from east to west, they're actually traveling, they're skimming right over surface ocean waters. And surface ocean waters get first crack at sunlight. So now you have this wind blowing over those surface ocean waters, and what it's actually doing is it's actually causing those waters to be skimmed off the top and pushed further west. Basically what happens is the warmest surface waters end up getting blown over to the western half of the Pacific Ocean. And so what ends up happening is you get this really large body of very warm water in the western half of the Pacific Ocean. And warm water leads to warm air. Warm air rises. As warm air rises, it expands, cools, and condenses, and that creates thunderstorms and stormy weather. So typically what happens is the trade winds blow from east to west. All of that warm water gathers up in the western half of the Pacific, and that creates warm rising air and very stormy weather. Now, on the other hand, in the eastern Pacific, all the warm water has been pushed away. What's left behind is this cooler water from below that rises up, and this actually causes this thing called the thermocline, basically the boundary between warm surface water and cold deep water, to rise up as well. So what we end up getting is in the eastern half of the Pacific Ocean, we end up getting a lot more cool water. Cool water leads to cool air. Cool air is sinking air. And so in the eastern half of the Pacific, we have sinking air, and therefore sinking air compresses. You don't get clouds in this case. And so typically what we end up getting in the eastern Pacific is much calmer, clearer, I almost like to jokingly say sunny weather. So you get stormy weather in the western Pacific and clear and boring weather in the eastern Pacific. And so this is the entire component of the Walker circulation. And this is actually the neutral case. This is the normal. I like to jokingly call this la nada, the nothing. Basically, nothing is happening here. In this setup, all that we have is warm ocean waters in the west, cold ocean waters in the east, rising air and stormy weather in the west, sinking air, and therefore sunnier weather in the east. Now with that said, what happens in an El Nino? Well, an El Nino is actually a phase of the Walker circulation. And here's what happens. Those trade winds that were skimming all of that water and moving it to the Western Pacific actually slacken off, and in many cases even reverse. And the reversal of the trade winds then causes warm water to begin to collect over the eastern half of the Pacific Ocean. And what this does is this actually causes the Walker circulation to essentially reverse. So rather than getting this big buildup of stormy weather in the Western Pacific and dry weather in the Eastern Pacific, we end up getting a nice buildup of warm water in the Eastern Pacific and stormier weather in the Eastern Pacific. Now what's interesting here is that we typically think of El Nino as wet and wild here on the west coast of the United States. And that's because that's typically the case here. However, during an El Nino, the Western Pacific, areas like East Asia, so I'm talking about China, Japan, Korea, Taiwan, the Philippines, and then further south, Australia and New Zealand, they are usually experiencing record drought during that time because they've lost that warm rising air and it's replaced by cooler sinking air. So they don't get as much rain, they don't get as much stormy weather. Meanwhile, us here in the Eastern Pacific, over where the United States is, we get a lot more stormy weather. And so that's what an El Nino is. That's what an El Nino is. Now, with that said, there's also a case where rather than weakening and reversing, the Walker circulation actually strengthens. And when this happens, even more cold water from the Eastern Pacific rises up, and even more warm water collects in the Western Pacific. And in this case, the Walker circulation intensifies. This is what's called La Nina. So basically the opposite of El Nino. This is called La Nina. And so the Western Pacific becomes even stormier, Eastern Pacific becomes even drier. It becomes even drier. Now, a part of this assignment, you'll actually look at some of the conditions that are caused by El Nino and La Nina. And at the very end, you're also going to look at a La Nina statement, or what's called an ENSO statement. So all three of these components of the Walker circulation, all three of these conditions, are part of what's called ENSO, El Nino Southern Oscillation. And so basically that just explains this oscillation, this change in the Walker cycle. Now with that said, we've actually had some pretty notoriously strong El Ninos in the last 30 years. We had one in the early 80s. We had one in the late 90s. I remember that one pretty vividly. We had another supposedly strong one in 2015. I like to call it a fail Nino because it didn't really give us the kind of rain that we expected. But the point's still there. With that said, what we've actually learned is that we need to know, is there an El Nino or a La Nina or neutral conditions happening? So what has actually happened is the National Weather Service, part of the National Oceanographic and Atmospheric Administration of the United States, along with the Japanese Meteorological Agency over here in Japan, decided, we really need to figure out what's going on here, and we actually want to monitor it. And so what we did together was create a series of buoys called the Triton Array of buoys. So the Triton Array of buoys. And basically all that it is it's a set of buoys that were set at different coordinates along the equatorial Pacific, and they have just a few key monitoring instruments in them. Typically things such as air temperature, wind direction, wind speed, and sea surface temperature. And so each one of these things then tells us, is the equatorial Pacific in an El Nino, a La Nina, or neutral conditions? Before I move on to the next part of this, though, and show you some of the maps that are a result of this array, I do want to mention one thing that typically confuses people. And that one thing comes from the concept of longitude. So longitude is actually how far east or west you are of a line called the prime meridian. And the prime meridian is a line that goes almost through London over in Europe. Now with that said, longitude numbers range from 0, which is right on the prime meridian, to 180 on the other side of the world. Well, unfortunately, this 180 degree line happens to go right through almost the middle of the Pacific Ocean. And what this does is this actually splits the Earth up into two hemispheres. Everything over here is what we call the Western Hemisphere. This is all the areas west of the prime meridian. Meanwhile, over here, this is the Eastern Hemisphere. This is everything east of the prime meridian. Now here's what's confusing about this, though. This map is still as true as every map I've given you in this class. West is still on the left. East is still on the right. And so I think it's very possible, and I'll actually show you an example in a moment, I think it's very possible to see those longitude coordinates and totally confuse yourself. So just say it again, write it down on a piece of paper, get it tattooed on your body if you have to. West is still the left side of the map. East is still the right side of the map. The coordinate changes from Western Hemisphere to Eastern Hemisphere, but that's not because you're going east. It's just because you've now gone so far west that you've actually entered the other hemisphere. That's all that happens there. So here is one of these Tau Triton Array buoy data sets. And so here's what it is. Now again, let me just say one more time. This is still the western half of the Pacific over here. West is still on the left. Now I know that as you continue traveling west, you notice that the coordinate changes from west to east. That's not because this over here is east, it's just because this area over here is now in the Eastern Hemisphere. It's in the Eastern Hemisphere now, but it's still on the western side of the Pacific Ocean. So I know that that could be confusing, and I just don't stress as much about these numbers other than the fact that they are a coordinate system. Just know west is still on the left, east is still on the right. That will always be true in this class. Okay, now with that said, let me actually tell you what's going on in these two maps. So the first map up here, this first panel, has three very important pieces of information. The first thing it has is the monthly mean temperature at different locations of the ocean. So what you see here, monthly data November 2015 and means, that means these were the average temperatures for that particular month. These were the average temperatures for November 2015. And just like any other temperature map that you've seen, the darker the red, the warmer the temperature. The greens and blues represent colder temperatures. And so this top panel is just telling you what the current observed temperatures are, the mean observed temperatures for that given month. These alone can't tell you if you're in an El Nino or a La Nina. Unfortunately, they can't tell you. The other thing that they do tell you, though, is what direction the trade winds are blowing. So these wind arrows actually represent the direction and the speed of the wind. The direction is simply where the arrow is pointing, and the speed is how long the arrow is. And if you notice, for the most part, the winds here in the eastern half of the Pacific are very strongly blowing from southeast to northwest. And then over here in the central part of the Pacific, you notice that the winds become very light. They become very light over here. Okay, so that's everything you need to know about this top panel. This alone cannot diagnose an El Nino or a La Nina. What can, however, is what are called anomalies. So, an anomaly is simply a difference from the average, a difference from what's normal. So think about it like this. Let's say I were to give a test and the average score was 80%. Somebody who got an 85 on the test would have a positive anomaly of 5%. They were 5% above average. Somebody who got a 75 would be 5% below average. I hope that makes sense. So when talking about anomalies, we're talking about the differences from the average. And this map down here is all that. It is the anomalies. It actually shows us where are temperatures higher than they should normally be, or where are they lower than they normally should be. And that's what we want to see when we look at an El Nino. When we look at an El Nino, we want to be able to see, okay, are the temperatures warmer than average? Are they at average, or are they cooler than average? And here's what you would look for. Just like with regular observed temperatures, warm anomalies are going to be shown in darker oranges and reds. Cold anomalies are going to be shown in darker blues and purples. And then pretty neutral anomalies, meaning like near zero, are going to be shown in green. All right, so let me actually help dissect this map real quick. One mistake that a lot of students make is they identify, so you'll be guaranteed given a question of what were the highest anomalies. And a lot of students will find the largest value of these iso lines, these isotherm lines, and they'll say, oh, well, that's the largest value, so that's the largest anomaly. But remember, an iso line actually divides areas of higher temperature anomalies from areas of lower temperature anomalies. Here's what that means. This right here, this is the largest isotherm, and it represents a 3-degree temperature anomaly. But remember, everything on one side of it, particularly on the outside of it, actually has anomalies less than 3, and everything on the inside of it has anomalies greater than 3. So when you're actually taking a look at these maps, be very, very careful to not say, oh, well, the highest number is 3, therefore the highest anomaly is 3. Nope. If it looks like a bullseye, whatever is inside the bullseye is higher than 3. It's higher than 3. Now, one of the things I should mention, you don't see an additional 3.5 anomaly in here. So guess what? That means that these anomalies are between 3 and 3.5. They're between 3 and 3.5. And these are all positive anomalies. Now, you may also be asked, where are negative anomalies? A negative anomaly map would simply look like this, but instead of the yellows and oranges and reds, you would see more greens, blues, and purples. But it would be the same idea. Okay, now, putting this together, when we want to identify an El Nino, we want to look for an area of large positive anomalies, specifically in the eastern part of the map. And if you take a look, we see that here. We see this large body of oranges and yellows over here on the right side of the map. That represents an area of large positive anomalies. This is a textbook El Nino case. Now, on the other hand, when we want to identify a La Nina, we would actually want to see something that looks blue over here instead of orange, yellow, and red. We would want to see negative anomalies. And those negative anomalies would then indicate, okay, we're in a La Nina right now. The last thing on this map are these arrows. These are what are called wind anomalies. basically all that these represent is how abnormal are the winds. And, are they weaker, stronger, in what direction? And if you notice, the wind anomalies themselves are primarily directed to the east, and they're relatively strong. Whereas over here in the eastern half of the Pacific, the anomalies are very weak. This represents relatively normal wind flow, whereas over here, relatively strong wind flow. Relatively strong anomalies, relatively abnormal wind flow. And that's pretty much all you need to know for this assignment. So again, make sure that you keep an eye out for the largest number in that bullseye. That's not the largest anomaly. What's inside is the largest anomaly. And also remember, negative anomalies are large too. The larger the number, the larger the anomaly. So a -3 anomaly is larger than a -2 anomaly. So that's everything you need to know for this lab, and if you have any questions, comments, concerns, threats, or anything like that that you want to send my way, please feel free to drop me a line. I am here to help, so please don't hesitate to reach out, and I look forward to hearing from you, and best wishes as you uncover the beauty of El Nino.